In this lesson, we are going to talk about exponential and logarithmic models. The idea here is that we are using exponential functions or logarithm functions to represent a real-world situation. Exponential or logarithmic functions are used for exponential growth and decay, Newton's law of cooling, and logistic growth models. So for our first example, let's talk about bacteria growth. Bacteria grows usually in an exponential model. A population of bacteria doubles every hour. This is exponential growth. If you started with a single bacteria, in an hour you'd have 2, in 2 hours you'd have 4, in 3 hours you'd have 8, and so on. That would look like 2 to the power x minus 1, where x is the time, in hours. But let's say that we start with a culture having 10 bacteria in it. So at time 0, we have 10 bacteria. What would be the function to describe this population of bacteria? In general, exponential growth can be shown by the equation A equals P e to the RT. A is the amount of bacteria at time t. P is the starting population. R is going to be our growth rate, and relatively, we'll see what that looks like in just a second, and T is the time. So for us, our starting population is 10. There are 10 bacteria to start with. When time equals 1 hour, the amount equals 20. So we'd have the equation 20 equals 10 times e to the r times 1. Solving for r, we get 2 equals e to the r. I divided both sides by 10. And therefore, r equals the natural log of 2, because we undo the exponential function with the logarithm function. Therefore, we have a equals 10 times e to the natural log of 2t, and using our logarithm properties and exponential properties, we could also write that as a equals 10 times 2 to the t power. If I were to graph this population over time, we have a y-intercept at 0, 10, and then it continues to grow. So this is the point 1, 20, and then I'd have the point 2, 40, and so on. Our second example is talking about the amount of carbon-14. Carbon-14 is a radioactive element, and it decays exponentially. Maybe you've heard of radioactive decay. The half-life of carbon-14 is 5,730 years. So it takes a long time for carbon-14 to decrease in size. So that means that if P is the initial amount, that in 5,730 years, we're going to have half of P. So the amount would equal half of P when time is 5,730. So we set up the equation 1/2 P equals P e to the r times 5,730, which means 1/2 equals e to the r times 5,730. Undoing exponential functions is a logarithm. So we have natural log of 1/2 equals r times 5,730, which means r equals natural log of 1/2 divided by 5,730. Using the logarithm property, we could also write it as negative natural log of 2 divided by 5,730, which means the equation for the amount of carbon-14 that's present would look like A equals P e to the negative natural log of 2 over 5,730 times T. The fact that e to a natural log, they cancel out. We could also write this as P equals 2 to the negative T over 5,730. And here is our graph of the exponential decay. Our other point would be here, 5,730, 1/2 P. Notice that y equals 0 is our horizontal asymptote, which means that the amount of carbon-14 actually never goes to 0. It just gets closer and closer to 0. For our next example, we're talking about Newton's law of cooling. The equation for Newton's law of cooling is T, which is the current temperature at time little t, equals A e to the k T plus T sub s. T sub s is the temperature of the surrounding air. A is the initial temperature minus the temperature of the surrounding air. And K is some constant, which we call the rate of cooling. And it depends on the object we're talking about. You may be aware that metal things will cool off faster than wood. Okay. Think about the heat when you touch the heat transfer when you touch something metal goes faster than the heat transfer when you touch something that's wood. So, how long would it take for a cheesecake to reach 70 degrees Fahrenheit in a 35 degree Fahrenheit refrigerator? So 35 degrees Fahrenheit is the temperature of the surrounding air because we are in a refrigerator. We also know that it takes 10 minutes for the cheesecake to go from 165 degrees to 150 degrees. So that's going to help us find the value of K, the rate of cooling of cheesecake. So again, our equation is capital T equals A e to the k little t plus T sub s. T sub s equals 35 degrees Fahrenheit. A is 165 minus 35, or 130. And to find K, we are going to substitute time equals 10 minutes into the equation. And we know that the temperature after 10 minutes is 150 degrees. Solving for K, we end up finding that K equals the natural log of 115 over 130, all divided by 10. And that is approximately the decimal negative 0.0123. And, going out to 3 non-zero decimal places is a pretty good estimate. So solving for T, where we have 70 equals 130 e to the negative 0.0123 t plus 35, we end up getting t equals the natural log of 35 over 130, all divided by negative 0.0123, which is approximately 106.68 minutes. So an hour and 47 minutes is how long it's going to take for the cheesecake to reach a temperature where we would eat it. So these are 3 examples of exponential growth or exponential decay. If you are given a function that involves logarithms, we would do the same ideas because logarithms are the inverse of exponential functions.